All right, and thanks very much for the invitation and the kind introduction, DK. Always happy to come up here because we owe you for all the contributions that MVAPICH has made to our systems over the years. So yeah, what I want to do is talk about sort of our experiences over the last year and a half or so using MVAPICH on Stampede, but before that, to go through sort of the history of our partnership and where we think it's going next, and some new systems that we're doing together, and some things that might be coming down the pipe. So first of all, you don't stay funded long if you don't put your funding agency's acknowledgments on the front page. So most of what I'm going to talk about, well, it's funded by a whole host of NSF grants, but primarily the Stampede grant, which is actually in partnership with our colleagues here at Ohio State, and then some other grants that we've done directly with Ohio State. So can you guys still see that? Because I can't, so that's doesn't matter. So
I clicked the wrong button.
yeah, so there we go. So as I mentioned, we have really a long history of collaboration. Now I think we've been formally collaborating for about 7 or 8 years and playing with Infiniband, MPI, and MVAPICH concepts for 12 or 13, well, at least 9 years now, going back to 2005. And really, I think it's been a co-evolution because as new systems come online, there's always new development we have to do, and we sort of learn these lessons together, and that's why we value this partnership so much. So there's a lot. We'll talk briefly about Stampede, but Stampede, like a lot of modern systems, is getting increasingly heterogeneous. There's a lot more levels at which we have to optimize to make MPI or MVAPICH work well, and that's something we've done a lot on. And we have a new system that was just announced by NSF last week, Million, that talked just briefly about that will be the next stage in our partnership together. So as I mentioned, we've used MVAPICH on a lot of systems through a lot of years, and I'll cover some of them, but not all of them. But the things that have been uniformly and universally true throughout our partnership is once we sort of get everything on there and running, MVAPICH is consistently our highest performance MPI, and there's a lot of ways to define high performance MPI, but it's best at small messages, getting bandwidth for small messages, or mid-sized messages, the ones that people actually use. Usually gives us the best latency, usually gives us the best startup, and it's usually the one we turn to when we really need to get something done on a benchmark. People will come in and they say, I'm using my own crazy version of MPI, it's a vendor crazy version of MPI. And I have this code, and I'm sure it'll work on your system at scale, and it doesn't, and the way we fix that is switch to MVAPICH, at least half the time. So, it's always been our best MPI implementation on all of our machines. And it turns out this isn't just because we happen to pick the best hardware to run MVAPICH, right? That's not why you get success with these things. It's because of the way we've been able to work together in order to achieve high performance on these things. And in particular, despite what you might read on shiny and glossy brochures, none of this stuff really works out of the box when the system shows up on day one, especially when you're doing stuff at a new scale for folks. When you stand up one of these big leadership class systems for the first time, there's a phase of tuning to make everything work well. And if you're not in a position to tune, and you don't have the right people on your team to tune, it can be somewhat disastrous. So we're always tuning for, pushing the interconnects to a new scale. We've done the first of something with Infiniband several times through our history. And again, I should say probably that there's a co-evolution here, not only with TAC and MVAPICH, but with Mellanox as well, and a lot of the Infiniband stuff, because we're all working together to figure out what happens to new topologies and new scales. So there's always tuning to deal with the latest in the interconnect topology. One thing we work a lot on through the years is the change in what a node looks like and the intra-node communication. And that's still a challenge, something Jerome will talk about tomorrow. Is the latest stuff in intra-node, but when we started with MVAPICH, you had one core on one socket, so your on-node communication was pretty straightforward. And then you have, one core on 2 sockets, on each 2 sockets. You have one path to communicate, and then we went to, 4 cores per socket, 8 cores per socket, 16, 32 cores per node, and then we started hanging crazy PCI accelerators on the other end, and that level of communication on the node has become a bigger issue to work together on. And then finally, with this age of accelerators now, we have heterogeneous nodes, and lots of different paths that we have to communicate across to work well. And so tuning all of that has been key. And you really see dramatic effects, and not just on day one, but over time. And I'll go through some of that as we move forward. So let me just run briefly through our history. Some of you might have seen some of these slides before, with apologies, but I think it's worth going back briefly through how we got where we are. So, TAP started in Linux clusters in about 2000. I actually started in Linux clusters with the second one in 1993, in the early days of the whole Bay-old clustering movement, when just getting communication to work at all was challenge number one. I still think, the goal of the first cluster I built was to get a gigaflop for $50,000, and that's still sort of embarrassing at this point. But so now we're getting 10 petaflop scale, so 10 million times faster, but in a relatively short time. But most of us started, on shelves and in garages at 8, 16 nodes and sort of that scale, and that hides a lot of problems that you see as you start to scale up. So by 2003, we were building sort of several hundred node clusters, pushing the top 30. And like most folks, we sort of outgrew Ethernet pretty quickly, and so we were in the MirrorNet age in 2000. So in 2005, we started looking at, all right, at this point, keep in mind, I think 300 of the machines on the top 500 were not clusters. They were big iron, so they're predominantly some form of cluster now, and very few had NGX internet. There were a couple of dozen internet machines. The ID was really, I seem to remember, starting to mess around with the hardware about 2004. So by 2005, we deployed some. We started doing a few measurements. Everything all right? I'm not really going to use a pointer. Thanks, sorry. But so that's what I was saying. But what we found pretty quickly with what was the top spin InfiniBand implementation at the time is once you start growing, do some raw measurements, do some MPI latency measurements, it was a lot better, right? It was 5 or 6 times better latency than Ethernet. It was twice as good as any of the MPI implementations on MirrorNet in terms of latency, and latency is really the thing that drives us in a lot of ways. So we started doing some internal benchmarking, and you see that not only is, so the sort of pathological cases that everybody tests, those run a 64-byte ping pong, aren't really the useful ones for most users. And in fact, the really big message ones aren't necessarily either. But when you start having some reasonable sized payload, things start to matter. And what we saw is, sure, the latency was just as good or better at any message size in other networks, but the carrying capacity of the bandwidth, once you start putting a real payload into the message, was hugely different in terms of performance, 3 or 4 or 5 times better. So naturally, from about that point forward, every system switched to InfiniBand, which very quickly brought us to MVAPICH. And you see that latency and bandwidth was paying off in terms of real application performance as well. And at this point, we had a single system with all the same nodes. That's about, system was 128 nodes. We had some of them each with MirrorNet and with InfiniBand and GigE, so we could do real apples-to-apples comparisons. Can't do these at the scale we work on anymore, but at this point we could. And you see that as we scale out to a modest number of processors, again, this is sort of 1 or 2 cores per node. If we got, consistently better performance on just about any application we wanted to throw at it over time. So based on all these experiences at sort of small scale, we started moving this up to the couple of thousand node scale in 2006. We started using OFED, right, moved to the open stuff. And we made MVAPICH our primary software stack, and we did great things in sort of 2006 and early 2007. But at this point, we were sort of MVAPICH users. We were at the same time climbing up the scale. This machine, 1 star 3, 1 star 5 is coming next year. Was number 12 on the top 500. But we were really MVAPICH users. We were getting good performance, but we could do a lot better. And we didn't really realize how much we needed to be involved with the MVAPICH team until the next system. Because this was, I don't know, around 1,000 nodes. It was working. But then we got to Ranger, which was number 4 on the top 500, and where we really sort of deepened our collaborations with both the MVAPICH team and with Mellanox, really got into improving the subnet manager. So Ranger was sort of a behemoth, right? It was 4,000 blades, a few thousand square feet, a few megawatts, thousands and thousands of IV cables. I'll come back to that cabling. Or actually, we got a little lucky on cables that we had just one core switch, or two for failover, but one central core switch for the whole system. It was a 3,456 port InfiniBand switch. They don't build them like they used to, source data, but they used 12x InfiniBand cables, and we had pretty nice integration at the node levels. We actually only had one cable for every 3 nodes. So 4,000 nodes, only 1,500 InfiniBand cables. Contrast that to the current generation with Stampede with 6,000 nodes, 12,000 InfiniBand cables. Nonetheless, cabling still turned out to be a huge problem. By the way, before you start tuning your MVAPICH, make the cables work. So it sounds really simple. It sounds really obvious. We have now, it's a relatively small system, we have now had one of our 9 generations of InfiniBand systems where we didn't have a huge cable problem. So we've had like 3 where we didn't rip out all the cables and start over. So this was not one of them. That is the 2nd generation of cables on Ranger pictured there. But a pretty big one, and of course, everything works when we first brought it up, but some things were painful. InfiniBand speeds were like 30 minutes, right? So that's how long it took the subnet manager to figure out the topology, which doesn't sound too bad until you realize that happens every time any of the 4,000 nodes reboots. You lose a half hour while InfiniBand figures that out. That became 45 seconds or something later in the project. But we also realized we needed some serious help tuning this, and so at the MPI layer. So this was went into production early 2008, but of course most of the work then was all through the fall of 2007, and a perhaps not entirely chance encounter, but Carl Schultz who I stole this particular slide from, met DK. And started working together at Cluster 2007, which is part of the plug for the benefits of actually showing up at conferences, and in particular smaller conferences than, say, supercomputing, where there's 15,000 people in the room. Is these smaller meetings with a couple hundred folks, occasionally really significant collaborations get started there. So Carl Schultz, Tommy Maynard met with DK at this particular meeting. I was there, but I can't claim any credit for this. Happened to be in Austin, and this is a collaboration which led to what at this point 6 or 8 different funded awards, and 7 years of really fruitful work from this first encounter. Starting and so 4,000 nodes, 16 cores per node, 4 quad socket, quad core processors on each node. So 63,000 plus MPI tasks we were starting again in the 2007 era. I put up a slide the other day talking about some benchmarking for HPCG, or one of the new benchmarks, and said, so this was a small run at 78,000 tasks, and I realized how the scale has changed in just a few years. Big run's like 500,000 MPI tasks now. But anyway, at this point, we were trying to get out to 60,000, and we needed to scale startup, and of course there were some things that were interesting there, and we needed to start thinking about, we had this crazy quad socket, quad core configuration. We had some unbalanced links. Not every processor was linked to every other processor at the same rate. It was supposed to be a full crossbar. These were Sun nodes and the AMD Barcelona processors, but a couple of the links got stolen to do I/O and to do InfiniBand. So some sockets to some other sockets had different rates. But from an MPI perspective, if you're doing a collective, well, 15 other ranks are on that same node. That doesn't involve crossing InfiniBand, and then everything else is, of course, off-node, and some sockets are going to do faster communication to InfiniBand than others. So we have a lot of what I feel like are really fruitful collaborations. One, scaling startup, where we could launch a full system job in just a couple of minutes once we got the fabric to settle. And also, 30, 40, 50% performance improvements in the collectives on node, over the first year or 2 of production. So the system really helped. And the MVAPICH team started out really, we put Ranger together before we really knew these guys. We weren't a funded partner initially in the grant, and yet still worked night and day. We'd say, hey, we're running this collective. Here's the performance we see on now these new 16-core nodes versus the Lone Star nodes, and we'd get back a new version like 3 days later that would have a patch to that and make a big difference in the way we could run on those nodes. So dramatic improvements over time. I'm suddenly realizing I don't have a clock. Yeah, fine. So one of the big improvements that I mentioned is, real messages are sort of at the mid-size, right? 0-byte latency is interesting, but not really that useful for applications. Latency sending 64-megabyte messages is what we all want to see for, showing off fancy benchmark numbers, especially if you're talking the file system. But in fact, real applications don't do that. Most messages are somewhere at the mid-scale. So as we improved from Lone Star and new MVAPICH versions, this is just between 0.9, 0.8, and 0.9, 0.9. In MVAPICH, we get sort of the same shape curve as the messages get bigger. So we're still, same bandwidth at small messages, same bandwidth at large messages. We're using the same, SDR Infiniband technology at this point. But the real advantage and where the optimization took place is the size of the message that you needed to get that bandwidth got a lot smaller, which affects a lot more applications, right? So we came up this curve. If you're doing 100 or 1K messages, you're doing way better than you were in the previous generation because it's at your message size, the difference between these curves. So this looks like, well, we shifted things to the left a little bit. Woohoo! It turns out that that's really a big deal over time to make those kinds of shifts, because lots of applications do better and better. Hey, there it is. Thanks. So just another comparison. Again, optimization on, Synchroncy, pairwise, and then broadcast collectives, and looking at across the different MPIs. And on Ranger, we still supported every MPI under the sun. And we still do this a little bit. Okay, it was a sun, so we actually had sun MPI, but that was not intended as a pun. Trust me, anything's funny, it's purely by accident. We had, 5 MPI stacks on the machine because every vendor wanted to have theirs. There was Intel MPI, Sun MPI, which is fortunately gone away. We had Open MPI and MVAPICH, and there were some other competitors at the time who were lost in that there's Platform MPI, just, one after another. Now we just pretty much figure when MVAPICH works, the machine's done. We don't bother anymore. But at this point, we still have all these stacks. And you see, again, pretty dramatic performance improvements in both bandwidth, some bandwidth, the higher curve is better, and the actual time, so there, the lower curve is better. And really across, I could go on and on with these graphs, and I might have for one more slide. No, I stopped. For broadcast, for collectives, for point-to-point, for really any MPI function you have, once we'd gotten together with the MVAPICH team, we really got optimization so that across the scales of message sizes and across the scales of one node to many node and on-node communication, things were dramatically better. So at this point, we figured, well, we've done this at large scale. It's easy. We should just do a much more complicated machine. What could go wrong? So that takes us to Stampede, which is where we are today. Again, funded by NSF in September of 2011. At this point, we knew enough to bring DK in as a partner from day one, as a funded partner. We actually added him in midway through the Ranger grant, and every grant since then. But so we built Stampede in 2012. We got the award in September 2011. I'm not going to go through the sort of building the data center, but we sort of frantically built an extra 15,000 square feet and 7 extra megawatts of power to bring this in. Started deploying in August of 2012. The parts we needed to actually deploy the PHYs showed up in September of 2012, and we went into production in the beginning of January last year. So now we're 19 months into the production life of Stampede. It has been remarkably successful. I'll talk a little bit about the project before we get just to the NPI pieces of it. We hit service units are essentially 4 hours in the Exceed lingo. We went past 1 billion delivered in July. So and also we hit probably haven't quite hit it yet, but we're very close to the 4 millionth job. I think we're around 3.9 million today. Ranger, which ended up running 5 whole years from early 2008 until overlap with Stampede for being on strength 3.2 million jobs in its entire lifespan. So, and I think, what, about 1.6 billion hours. So, but hitting 1 billion in a year and a half is pretty impressive. You know, there are many reasons that supercomputers are better than clouds, and I don't really need to go on that soapbox now, but I would point out that also our, if we were to turn the machine off today and not use the remaining 2.5 years of useful life, our per hour delivery cost is cheaper than Amazon. With advanced interconnect, with fast cluster file systems, with a team of partners to help us tune it, with scientific support, we're still actually lower cost. Plus, you know, on many codes, our service units are worth 5 or 6 times what an Amazon service unit's worth in terms of the performance you can get because of the interconnect and the MPI stack. So, so anyway, very successful. I'll do a few more stats and some of the sort of types of projects we're doing on it. But just at a high level, this is what made this one complicated. We only scaled up about 50% in node count for Rangers. We went from about 4,000 nodes to 6,400 nodes. We've done some systems in between that I skipped over. But you know, Ranger was an SDR Infiniband fabric. This is an FDR pure Mellanox fabric. And at this point, we've drunk the Kool-Aid, right? Not only did Mellanox make the chips, which was true in Ranger, they made the switches, the HCAs, and everything else. So about 100,000 cores we've gone to a dual socket node, so a little over 2 petaflops of peak performance from the base cluster. But we also had this co-processor component, this requirement of solicitation, I'll dive into it, and we went with the Xeon Phi, so we got another 61-core processor sitting on sort of the wrong side of the PCI bus, occasionally 2 of them, to get us another 7 petaflops of performance. So if you add those up, there's about 425,000 Phi cores, there's about 102,400, who's counting Stampede Bridge cores, pure Xeon cores, so more than 500,000 cores. Phis are 4 hardware threads per core, so to really fill up the machine for max performance, you need 1.5 to 1.8 million threads. Because of some of the limitations of Phi, we don't actually recommend doing that with 1.8 million MPI tasks. But you're still going to need tens of thousands of MPI tasks to get anything resembling good performance. And of course, there's a little more heterogeneity. We always have that's sort of the big homogeneous compute partition, but there is a large memory subsystem. There's some GPUs mixed in there just to make life more complicated, but that's Kepler K20s, Kepler K40s. And then, of course, there's all the login, data mover, and various sundry other nodes, which are in fact bigger than the clusters we used to have. We have 70 or 80 auxiliary servers attached to the cluster one way or another. We used to build 70 node clusters, but and then a pretty big storage subsystem, also all InfiniBand driven. Initially 14 petabytes, we've added another 20 petabyte file system to it, so we have about 35 petabytes of disk hanging off it now. The first file system was 150 gigabytes per second. If you add up across the file systems, we have about 250 gigabytes per second in and out of the machine now. But there was a requirement in the solicitation. The funding was actually split in 2 parts. To have one, replace everything that was going away with Ranger and the other NSF-funded systems that were disappearing in the time frame. But then do what was listed in yellow, a major new innovative capability component to science and engineering research, and for that, we went Xeon Phi for reasons that over the last couple of years have become clear. And the plan at the time, and I'm going to talk about the new plan before we get there, was to do 1 Phi per node, which we did during initial deployment. We then went back and decided to experiment with 2 Phis per node and a few hundred nodes. So we had a couple with multiple Phis. You now have 130, 140 cores to deal with on a single node, 2 different PCI slots hanging on 2 different processor sockets to balance communication across. And an injection of second generation Xeon Phis. This is the part we've actually changed. We're still going to have an injection of second generation Xeon Phis, kind of a somewhat different form factor that I'll get to. But this was sort of disruptive to us and to the users in the programming model, in that just start an MPI task on a node and have 1 binary was no longer the primary mode. In fact, there's several ways to program this that I'll go through. But if you simplify everything around Phi, and in fact GPUs, right, all of them are much looking at the inevitable future of swapping off complexity in circuit. Well, all of them are trying to drive down power per operation. And nobody has a good way to drive down power per transistor. So whether you're buying GPUs or PHYs or an accelerator, you're trading circuit complexity for more parallelism to get that power per socket that we're targeting. So, in a nutshell, the Xeon Phi is lots of cores, but all the cores are slow. Because, one, getting the clock rate down is the #1 way to save power. So it has a slower clock rate. But two, cores are much simpler from a circuit's perspective, because if your power per transistor is fixed, the best way to improve power is to reduce the number of transistors you use in a given circuit. So a lot of the branch prediction, out-of-order execution, other stuff, sort of modern processor architecture vanished, and sort of turn back the clock on some of that. But they have long vector units, so in that sense, they look somewhat GPU-like, right? Simple processing elements, a whole lot of them, pack them on a die at a lower clock rate to get more performance. So one of the reasons we think that is we feel like this foreshadows pretty much everything you're going to see in future processors. And in fact, even if you just look at the evolution we've talked about now, we started with 1-core Xeons, and we've gone through 2 and 4 and 8, Ivy Bridges 10, and now Petascale a couple of weeks, and more. The one after that would be more, and start thinking out to, 4 years from now, 2018, we're going to see 20-something cores likely on a Xeon socket, and multiple sockets. So many cores, many levels of memory. Essentially what's going on, but you see that this is coming. So we put these parts in to start moving users in this direction. But of course, like any new technology, there's growing pains. So I'll come back to that. But let me just say, big team that takes to put together this. TAC is the lead partner, and so we get to run the cables. Is really what that means. Oh, and write the reports. That's my primary job, is to write reports to NSF, as far as I can tell. But Intel and Dell and Mellanox were our vendor partners, all of which were essential to making this actually work. And then we had a set of academic partners presented here in alphabetical order that each have their roles. Of course, Ohio State for MVAPICH support is key to make this work. And then just timeline. There's, these really become, decade-long potential projects when all is said and done, because it takes 6 months to review a proposal, and 3 months after that to get a contract out, and about a year to negotiate the final terms. So things happen years before deployment. But so the solicitation came out December 7th of 2010. We submitted the proposal in 11. We got awarded at the end of 11. So started delivering the system August 1st. At the start of operations in 2013. We'll run at least through 2017 in the life of the system. And then potentially there will be a Stampede 2, which will add 4 or 5 years to that time frame. So as I mentioned, at this point, we feel like Stampede's been remarkably successful, although it's also a journey, like all of these systems. But I mentioned we've delivered 1 billion service units already, 3.65 million jobs. The diversity of what we run is one of the things that makes this not hard, but in many ways it's fun. But it's a very different environment that we try and run on Stampede. You want me to switch?
No.
Okay, good. So versus the type of environment you would see on a Department of Energy system, say a lab system, right? Most of those have dozens of projects, maybe 100 users, couple hundred users. We have a huge diversity of projects. I'll touch on 4 or 5, but already on Stampede, there are 1,771 different funded projects around the country that have run a job on the system. We have like 8,000 accounts, but there are 5,085 actual humans, or actual login names. Lord knows how many humans are associated with this. The policy's one, but that never really works. But 5,085 individuals who've actually submitted a job to a production queue, right? Not who've just got an account or logged in. That's how many have done something. We're running above 90% up, 97% uptime. Our contractual target is 96% for full system availability. Defined as both the time that the full system is available and the percentage of the full system available at any given time. Of course, the support load on this is pretty substantial. We're at 5,006 tickets, and that's a curve that also increases over time. So we're pushing 500 tickets a month. We resolve on that. We've had more than 2,000 users come to training every year on this, and that doesn't count online training. That's just what, synchronous instructor in front of the room type training, about 50,000 online. So 2,000 users, and we're oversubscribed by about 5 to 1. So it's a pretty popular system within the community. I get, we get more requests than we can possibly handle through the formal process, and let's just say there are informal requests that come in every single day for additional time. So that's sort of on the base system. We've also seen some pretty widespread adoption on the Xeon Phi. Now, keep in mind, we were sort of bootstrapping an ecosystem with Phi, and part of it was, the contract and the solicitation specified, all right, be in production on January 13. That was what was released in the solicitation long before we picked Xeon Phi. That was, shall we say, very close to the beginning of the Xeon Phi lifespan. In fact, they didn't start selling them commercially until July of 2013. So they've only been out in the commercial market for a year. Obviously some customers got them early. We were getting them. They have dates on them. It's like buying theaters. You have born-on dates on your Xeon Phis. They were coming out of the factory, and 10 or 12 days later, we were installing them from the very first runs. So as a result, most of the developer boxes hadn't made it out before we got our system. So it was really brand new to almost every user when we got them. So for many users, they saw Phi for the very first time when they got their Stampede account, right? They never had any chance to do in-lab or in-house development. Normally you want to sort of build from the desktop up in these ecosystems, and that's sort of where we've used them for about 12 years. But for a lot of people, it was like, oh, there's this Phi thing, what do I do with it? So wasn't supported Petascale starting out. But despite that, in the first 18 months of production now, we've had more than 800 people actually run a Phi job through a production queue. And we don't actually track in the development queues because the development queues all have Phis and they're all set up to run Phis all the time. So the development jobs can be a Phi, they can be not a Phi, et cetera, et cetera. So we just look at what's called the normal life queue to get these numbers. So we know 800 users have made it to the scale of production jobs. We know we've run 100,000 plus production Phi jobs, and we know they're across about 300 different projects. So, relatively big penetration into our market space. So a little bit about how we use them. So one thing that we're a fan of in the Xeon Phi is, for the most part, the environment is very familiar. It's pretty much x86-like. Generation or two from now, it'll be binary compatible with everything else. All the other Xeon chips, we're not quite there yet. But you can use an offload model and treat it like a GPU. I'll show you some quick code for this. But you can also just run it native. You can log into it, you can run a debugger, et cetera, et cetera. It runs Linux on there. Increasingly, a full Linux, we in fact have, you can. It's not a recommendation, let me be clear. You can run Perl on a Phi natively now, if you really choose to, buy an expensive high-performance chip and find a way to slow it down. You can run Perl, you can run Python, and all the scripting languages run natively on Phi. But most of the ways to use it, we have what we call native mode, which is pretend the host processors don't exist, log directly into the Phis, and run MPI jobs that cross to other Phis. We have symmetric mode, which is run MPI tasks on the host, make the communication between the host and the Phi strictly through MPI. And set some MPI tasks on the host, some on the Phis, and do that across the cluster. Have, Xeon tasks, MPI tasks on one node, talk to Xeon Phi tasks on another node, all through MPI. And then offload, which uses sort of direct lower-level PCI communication. But almost every mode, traditional languages with OpenMP and with MPI. So we're still using MVAPICH as our primary fabric layer to truck across the Xeon Phi. So, and just quickly, by way of example, just to prove it exists, right? You can compile a code normally and run it. Little hello world program here. You can install it from Carl, but so this is a compile for SMD Sandy Bridge. So for the regular Xeon, you just run the Intel compiler, run your code, and prints hello here. The only thing you change to run on the mic is you just throw the -m mic flag On the Intel compiler, it makes the Phi binary, so if you try and run it on the Xeon at the moment, it doesn't work. 2 years it'll work just fine. But then you just SSH into Mike 0, which will name the Phi on every single node. Mike has been integrated for it's the family, so you use Mike and Phi, all their previous names, Nice Corner, pretty much interchangeably, but you run that same binary SSH into the Phi, and it notices that Mike, the environment variable is set on there, but it runs. So we have the same file systems out there. That's another little challenge to get performance out of them, but you can see your home directory, you can see the scratch directories, you can open files, you can do your I/O native. So native execution is really convenient, except you're probably set up to do 1 MPI task per core. You have 61 cores, minimum of 122 hardware threads that you want to run. So you start 120 MPI tasks in the 8 gig of memory on the card, and you find yourself somewhat limited. So in reality, you're still going to do some tuning. But it does work. And then your other model, and I'm going to come back and compare these two in performance a little bit later, so let me just show it. This is a quick little piece of Fortran here, but this is an offload model where we're using OMP, OpenMP offload directories, OpenMP parallel sections here, and you just add that line on the top, offload target, Mike 0, to say where you want to offload to, and away you go. So you can treat the host as the execution model, and so this case, PCI to the Phi, in the other case, you're going to use MPI, and therefore MVAPICH to talk to the Phi. So, so keep those in mind when I come back on some performance things. Let me just say a little bit about the life through deployment. There's always fun building out these systems. Again, the initial thing, we've replaced work with a much bigger file system, but we took the 14 petabytes of disks, we split it into 3 file systems, depending on sort of use case. Scratch is the big one. That's where we can hit 160 gigabytes per second. You scale out the cluster. This is another good way to test your InfiniBand fabric in great detail, and many thousands of disk drives that you want to shake out. But we've had great performance through Lustre. Cabling is the most underappreciated part of any supercomputing deployment. You run the cables, so conceptually that's a pretty simple concept. In practice, there are so many different things that can go wrong. It's sort of hard to imagine. And having it done naively is the source of more performance problems, and that installations that I've seen in various places around the world, and I can begin to count. But in this case, we're using the biggest switch Mellanox will build and sell you, the 648 port switches. Frankly, we love bigger switches. It's occasionally cheaper to build stuff out of smaller switches, but cable count goes way up, and the pain is just not worth it. So you buy the big switches. We have 8 of these core switches. We have a little bit of oversubscription. It's 20 to 16, 5 to 4 in the from the lease into the core. So we have 6,400 copper cables to get those nodes to each switches in the racks, and then the those are 36 port leaf switches, so 20 nodes plug into them, 16 cables come out, which gives us 5,100 plus, and there's extra ones for storage and stuff. Fiber cables, we go to the 8 core switches, and it's always been our policy to keep the vendors out of the cabling for the reasons I just mentioned, so we do all this in-house. I'll have some more pictures of it. We've been through the cable management wars before, so we spend, I shudder to admit how much time designing cable management devices, like racks with Sun and these earlier IB switches. They put some really great cable management, so we could run 1,500 cables to a switch and have it look nice and clean like that with the big cable arms and the large bend radiuses. You want 12-inch bends. You want to support the cable about every 6 inches so it doesn't sag. Little known fact, of course. Cables are going to heat up in the data center. The plastic gets soft. They sag. It pulls on the connectors. Bad things happen. But we're pretty fanatical about cable management. So that was Ranger. We did similar things with Stampede for a number of reasons. We went to all overhead cabling here, so we're going the other direction. But we designed fab, eventually these sheet across. But these side of rack and front of rack devices that we add on to manage cables were again the same thing. We're getting 12-inch pins and fiber to go around a corner. We We have these little supports that we add in every 6 inches. We bundle the cables together nicely and cleanly. We have rules about which side of the cable tray you're allowed to go down. Cables going in different directions so they never cross and get congested. I think I have some closer to finished ones to show down the line. Nonetheless, you replace a lot of cables when all is said and done. One of the reasons you want to have them so clean is that you're going to remove some, put new ones in, and if they're just a big messy pile, you'll never get out to them. If you look back at the switch, the field replaceable unit on these, the thing you have to change out, not very often, they do occasionally fail, are these line cards in the middle. So you put it in a rack and you just run all the cables down in front of it, just sort of standard practice cabling, and then the line card halfway up fails. You unplug 600 cables to get to it, and you hope you put them back into the right port when you do that. So that's why we have all these designs to come in from the sides, so we can slide a line card out, just unplug the one line card, and put other ones in. Again, if it feels like I'm spending a lot of time on the really hard concept of plugging the cables, it's learned through painful experience. So we'll get back to that. There's always new things you learn about the processor and the kernel and the motherboard. This is not a Phi thing at all, but this was just latest Linux kernel on the base host. We always run stream as one of the things we run, both to accept the nodes, but then to requalify them every time they go back into production after adding an update or doing a change. And so we run the stream and you get a number, and of course these are digital circuits, so it's always the same, except that it's not. They actually vary from chip to chip as to what the performance is by 3 or 4%. It's more than about 4%. There's something wrong. But we were getting, bad data around the 6,400 different stream numbers, and they sort of group around a couple of % apart. Analog still does play a little bit of role in what goes on in real circuits. But we bring back, every time we qualify them, they go in, they'd be pretty consistent. But then users would complain a little bit over time, and we found that if we didn't do a reboot, and we just went back and ran a stream 5 or 10 days later, initially, the performance would change by like 20 or 30%, just for leaving the node on for a week and running. It turned out in some of the newer kernels, file system caching does interesting things to your memory bandwidth over time. So again, you run, Bill would know the exact number, but in the epilogue strips, when you clean up a node after a job, before we hand it off to the next job, we actually do a couple of hundred things between epilogue and prologue the nodes to check for file systems being mounted, and check this, check the other thing. One thing we started doing was flushing all the caches, all the file system caches between each job, and that got us back to the banding you want to see there on performance. But it does drift an amazing amount. Same thing as core count increases, and this affects how we tune MVAPICH, but placement of tasks start to matter a lot. Again, things users don't think much about. We actually do a lot of affinity settings for users as one of those many things we do in the prologue scripts is to set these up. But you're to the point where you can really affect your job performance by how you place your tasks if you're not using every core, or even if you are using every core, you need to think about locality. When you're tuning MPI, just think that's one setting in an environment variable, or the default is actually a kernel setting, is how you lay out threads. This is around 8 threads on a 16 socket node. Compact will run your MPI tasks for process 0 through 7 all on one socket. Interleave will put them across. And as you might imagine, there's not enough memory bandwidth to feed them all. So if you look at that 8 task case, it's 2 to 1 difference in performance that you see to memory if you don't do it. The fabric, fortunately, is predictable and is what we want, and it's getting better, right? Because as we move from SDR in Ranger to QDR in Lone Star 4, which I didn't really talk about, to FDR and Stampede, we're seeing both things that you want to see. The flattened out performance is at the advertised rate and getting better, and over time these curves are coming up faster, which is also, again, an important improvement in where the knee of that curve is. And so that's getting better. Latency is sort of spectacular. We're at a microsecond in rack. So across the switch, we're at 2.5 microseconds. Worst case, there's 100 meters of fiber in that worst case. So you're getting a few hundred nanoseconds from speed of light in the fiber. That's actually not getting better generation to generation of the technology. It's really disappointing. So the physicists have let us down again. But we're getting pretty close to where if we want better latency, we have to build smaller machines, physical footprint. So a substantial chunk of it is getting cable induced, or speed of light induced. But you do notice there's a pretty big difference depending on where you are in the machine. And one of the grants we work on together is placing MPI tasks to make that work. A little bit on the benchmarking. So clock rate is just sort of an advertised number. It's like miles per gallon now. They put it on the window, and that's the last time it actually matters is when you buy the car. So because everything has a dynamic clock rate nowadays, this is sort of an interesting behavior. You know, you do your scaling for impact. This is single node. I'll show full system. But you know, number of tasks per node. Remember, 16 cores on a node, 2 8-core sockets. When we're getting 120% of the theoretical peak at small numbers, and that's because these 2.7 gigahertz chips don't really run at 2.7 gigahertz. They run at whatever thermals will let them run at. And so 2.7 gigahertz is sort of, you know, on a normal day in April when it's 68 degrees outside, and when it's fall, it runs at 2.7 gigahertz. But in fact, in one core, when most of the processors idle, it runs at 3.5, right? It's like roads. You know, you build a big highway, and if you're alone on it, you can go really fast. But as soon as you really need it, and there's a lot of cars on it, everyone slows down. So same behavior. The clock rate drops as you get to about 8 tasks. You're really running at the rated, you know, window sticker frequency. In fact, we've discovered in our data center the way the PHYs fit in. You know, putting in those racks with 2 PHYs per node, we have 600 watts of power walking through a very small brick that we're trying to cool. So we keep the data center pretty cold. In fact, we've discovered we keep it so cold, they really run our 2.7 gigahertz Sandy bridges really run at 3.1, which makes benchmarking interesting on our system versus everyone else's, or any place where it's warm, or even on your desktop machine, because these run 20% faster when they're in the data center. So, so you get better than 100% at small core counts, but it of course flattens out. But a real testimony to how well the fabrics work nowadays and the MPI works. This is not the HPL number we submitted, because the HPL number we submitted, of course, was a hybrid run with Phi, you know, some of the Phis and some of the nodes. But this would be, forget the Phi. We just treated this as a big, huge Xeon cluster, you know, where everything's homogeneous and you can tune stuff. We got over 90% efficiency, which, you know, in the early days of clustering around Gigi, early MPIs, if you were getting 63%, you were really happy. And then, you know, it sort of drifted up into the 80s now is a good one. We get 91%, and not only can we get over 90%, we get it using only half or a quarter of the RAM on the node. One of the tricks to raising HPL efficiency is run a really big system, use every byte of RAM that you have. The problem was, in the Ranger era, is to get a max efficiency benchmark, you needed like a 3-day HPL run, and you needed to use every byte of RAM. Now, we can run that in like 2 hours across the system, because we're not, you know, we're solving a relatively small system using a quarter of a RAM on the node, but we're still getting 90–91% peak efficiency. So that is actually a good indicator that your fabric is healthy when you can get those sorts of numbers. So, and of course, as I mentioned, we talked about latency. Topology matters a lot. Those are the switches full up cabled. We have about 75 miles of IB cable. We did use a fat tree, so you can see pretty rich fabric at the core. There are many schools of thought as to what the right topology should be. It depends a lot on the mix in your application of communications. So that's a torus for comparison from another system using some of the InfiniBand discovery. The torus is fantastic if most of your communication is nearest neighbor. You're doing a lot of finite element or finite difference stuff, and you're doing a stencil around them. We're paying a lot for a lot of connectivity at the core that you don't use in sort of nearest neighbor. If you're doing big all-to-alls or big FFTs, you have to come across the core. Yeah, it's sort of artist rendering of the fabric, but it's pretty easy to see that you really have to go from every point to every point. We're a lot thicker in the middle than a torus is. And this makes a pretty big difference. And so this is a slide stolen from Hari, who's sitting in here somewhere, or at least the graph is. But in one of our projects here, with MVAPICH, I need to finish up here, but you see that depending on where you place your tasks for collective performance, so this is, you know, selectively putting your MPI tasks in the right place around switches to maximize latency, to not overload any particular switch, we're getting a 45% performance improvement in collective performance just on integrating task placement with the scheduler once you get to some reasonable sizes. of MPI. So all wonderful things. So all of that was to day one on Stampede, and sort of where we were a year ago spring. And that, at this point, you pass all your acceptance tests, all your user codes run, people get reasonable performance. But there's still work that goes on over time, and the system gets better over time. This is one of the reasons we think it's really important that you have a team that you really want to work with for a long term and not a vendor who you want to get rid of as soon as you get the system running, because you're really going to be deeply committed over time. And so this is both the vendors, but particularly collaboration with MVAPICH. And so again, slides that you'll probably see from somebody else, also stolen from some work that Hari did, but the team did. So this is back to those programming models that I talked about. If you think about the offload model, this is the performance we get sending data from the CPU to the mic, and then from the mic back to the CPU. So this is copying data very quick for offload messages. So MPI is not involved. You should get 7 gigabytes per second across the PCI bus. We're getting 6, nice and balanced. If you looked at day one with Intel MPI here, and this is actually some numbers figured out here at Ohio State, and we do native or symmetric, and we start sending MPI messages across on day one, we were getting 5 gigabytes per second, not too bad, going from the CPU to the Xeon Phi, but coming back, we were only getting a gigabyte, having to do with various things about who was running the bus and who was doing the read and who was doing the write and what's implemented in the PCI controller. So that's, working, really not what you want. But that was sort of February, where we were at launch. But through our long and fruitful collaboration, this is where we got with Intel MPI through June, and this is where we got with MVAPICH through July of last year, where it's in fact better than the offload case, right? The native PCI mode, much closer to what you should really get out of your PCI bus, and almost perfectly symmetric and coming up a whole lot faster than MPI. So all of this is stuff that nobody saw coming because we didn't have the PCI controller implementation until the system launched. And we didn't know that some paths were going to work differently than some other paths and what the low-level drivers were to get there. But over 7 months of the production life, things got a lot better. And we continue to work on improvements. And in Jerome's talk tomorrow, he'll show more. But the mic software stack keeps changing. What we can do on Node, I think Jerome's going to talk about some cross-memory attach optimizations that he's again doing jointly with the folks up here. But things keep improving. And this MVAPICH mic that we developed through the project is now actually available on other Phi systems as well. So I'm at 54 minutes. Let me just speed through a couple things. All of these changes we make at the system level that give us nice performance graphs have real impacts on real science for a whole bunch of folks. And that is why we build them. So it's important to just come back to this for a second. These are just a couple of my favorite projects that ran on Stampede in the last 6 months to a year. This is Volker Brahm, who is an astronomer studying how much heavy metal was in the early cosmos and how it affected galaxies, which is somewhat typical problem. What I think is cool about this one is these are predictions that, one, we haven't been able to run before, but even if we could, we had no way to verify the results until the James Webb launches in 2018. So this simulation will make predictions that the James Webb will be the first device that can verify, first time we've been able to run them. And in fact, because it will say, hey, there's a very interesting phenomenon in this part of the sky, this computation is actually going to drive the James Webb mission for how the telescope is targeted over time. So, something that, years from now will still be having an impact on this multi-billion-dollar instrument once it's in the, flying however many thousand miles away in space, it's going to be flying. And how they use it is determined by this computation. This is some folks at Houston Methodist Hospital who, for various historical reasons, have faculty appointments at Cornell, but who found some signaling pathways in genomics, again, using Stampede, but, gene signaling pathways that are in common between a particularly aggressive form of brain cancer and Alzheimer's, and they're starting to look at cross-drug treatments, use Alzheimer's drugs for brain cancer drugs for Alzheimer's, et cetera, because of what they found here. This is from Michigan State, looking at flexibility, DNA repair mechanisms, all important stuff, all things that are way beyond the scale that you can do at the desktop. run on Stampede. This is one of our industrial partners. Technip does offshore oil platforms. They've replaced a lot of their wave tank experiments with simulations. They design, you probably haven't heard of Technip, but they're actually a pretty big company. They do the oil platforms for BP, for Shell, for Chevron, for Exxon, et cetera, et cetera. And they use Stampede as sort of their production modeling resource at this point. This one's an older one from the early days of the system, but particularly relevant today. It's about earthquakes in California, which there was a large one on Sunday. This is the rupture forecast, UCERT 3. And this one's significant, not only because they have a lot of earthquakes in California, but this particular set of simulations is what the USGS uses to set both building codes, and then in turn that gets used to set insurance rates. So if you have a building in California, how much it costs is a direct result of this particular simulation. So I'm out of time. Let me just say we're now working on a new system that, well, we're working on a lot of new systems, but this particular one was just announced. The MVAPICH team is a partner on, and it's going to be a test bed for cloud and computer science, led by Kate Cahey in Chicago. A big chunk of the hardware will live at TAC. In this system, we'll do things that we wouldn't do on a production system like Stampede, but we will let users get low-level access to look at how you ought to build clouds and the system design trade-offs. So we're going to take advantage of the SRIOB work, which I'm sure will be talked about by DK and folks, and how you use InfiniBand properly with virtualization and advanced networking. It will be the first system in which we will give users root. So that's kind of stupid, but we'll see what happens. And then finally, the Stampede upgrade. We're actually going to modify that plan from more Xeon Phi PCI cards to self-hosted Xeon Phi nodes in the next generation. So we're going to have an entirely new kind of fabric and new places for MVAPICH to conquer. I think I can skip the rest. You know, networks are going to change, but let me just say thanks to you for listening and sitting through this entire talk, and thanks to DK and team, because MVAPICH really provides an uplift for a huge number of people and a huge number of projects around the country, and we couldn't do it without you.